When people talk about the web, they often rely on spatial metaphors, as if data exists in physical rooms. But the internet is a series of access and indexing protocols determining how data packets route from a server to your machine. What we call the surface web is simply the data that standard search engine crawlers are permitted to index. This information is linked openly via public DNS, making it globally searchable. This visualization shows a network directory tree. The small open branch at the top is the surface web. Below it is the deep web, which makes up the vast majority of the internet. These nodes are shielded by gatekeeper protocols like SQL queries and authentication screens. The dark web is a specific subsegment of this deep layer. It operates on an encapsulated, encrypted overlay network that requires specialized software to navigate. These cryptographic protocols solve the mathematical problem of unlinkability. Standard IP routing dictates that every data packet contains a header. That header explicitly lists both the sender's IP address and the destination's IP address, allowing routers to pass the data along the correct path. Commercial VPNs attempt to mask this by routing your traffic through their server. However, if a global adversary is monitoring the network, they can observe your data entering the VPN and exiting towards its final destination. The VPN provider still holds the complete connection record. To defeat this tracking, cryptographers design systems around the principle of unlinkability. True unlinkability requires decoupling the identity of the sender from the identity of the destination across a public network. No single entity observing the connection can know both who is sending the data and where it is going. Achieving this means abandoning standard IP routing entirely. The construction of how data packets are assembled and forwarded at the network layer must be mathematically re-engineered. The architectural solution to this problem is network layer onion routing. To build an onion-routed packet, the origin negotiates keys with every node. It appends forwarding segments with routing instructions. The payload is wrapped in encryption layers, one per node. Padding bits are added to ensure the packet maintains a strictly uniform size. When this encrypted packet reaches the first intermediate node, it triggers the remove onion layer protocol. The node uses its local secret to decrypt its designated forwarding segment, reading routing instructions for the next hop. After verifying a message authentication code, the node strips away the outer cryptographic layer and pushes the packet forward. Because of this mathematical structure, an intermediate node only possesses the keys required to identify its immediate predecessor and its immediate successor. This layered encapsulation ensures that no single piece of network infrastructure ever holds both the origin point and the final destination data simultaneously. Even with flawless encryption, a global adversary monitoring multiple network nodes can still de-anonymize a user without ever breaking the AES ciphers. This graph demonstrates a timing attack called network statistics correlation. If an adversary tracks the rhythm of packets entering a node and finds a matching rhythm exiting a node further down the chain, they can connect the entry point to the destination. Forcing all packets to be a uniform size is insufficient if the transmission rate, the gaps of time between the packets, remains identifiable. The required countermeasure against this statistical correlation is end-to-end network layer traffic shaping. This requires routing logic called split onion packet. The node splits the incoming flowlet into one payload packet and one dummy packet. It pads both to the exact same size. This constant transmission rate completely obscures the actual data flow rhythm. Traffic shaping mathematically starves the adversary of the metadata exhaust required to perform correlation attacks, protecting the unlinkability of the routing protocol. Routing data anonymously is only half the equation. The other half is proving authorization to a secure server without revealing identity. Based on blind signatures, anonymous credentials let a client mathematically prove an internal state, like a valid access token, without revealing its value. To prevent double spending, the client reveals a single-use nullifier during presentation, which the server logs to update the access counter. The looming engineering challenge is migrating these anonymous credential systems to post-quantum cryptography standards like ML-Chem. This must be completed before quantum computers become capable of executing store now, decrete later attacks. Anonymous credentials provide the final layer of the network model, allowing users to authenticate and transact within the dark web while retaining absolute cryptographic privacy. Anonymity on the dark web is rarely broken by adversaries cracking encryption algorithms. It fails because of human operational security gaps. Surveillance systems rely on behavioral fingerprinting. This is the aggregation of microsignals and metadata exhaust leaked continuously by a device and its user. Overlay networks like Tor protect users by blending them into a crowd with identical configurations. Installing a custom browser plugin alters your footprint, making your connection distinct. Utilizing a personal operating system to access these networks presents an extreme risk. True anonymity requires compartmentalized, amnesic environments, like Tails OS or Winx, that erase their state entirely upon shutdown. Furthermore, underlying hardware sensors create a unique behavioral signature. Factors like battery refresh patterns, screen resolutions, and accelerometer data can identify a user across platforms, bypassing network encryption entirely. Relying on a mathematically perfect network layer protocol is useless if the endpoint device is actively broadcasting a unique behavioral signature. These tracking systems feed into an identity graph, a database built by brokers that maps isolated fragments of a user's digital life into a single cohesive profile. This highlights 3 isolated data clusters: work, personal, and secure. The fatal error is cross-contamination. An overlapping variable, like reusing an email prefix, creates a bridge between identities. This link collapses the identity graph, tracing anonymous activity back to real-world identifiers. Defeating the identity graph requires strict, uncompromising compartmentalization of devices, connection schedules, and aliases. Maintaining invisibility requires significantly more effort than downloading a single piece of software. True privacy on the modern internet demands a complex architecture, mathematically sound protocols at the network layer, and rigorous compartmentalized operational security at the human layer.